do part 2 of the RL circuits. Now let's move the switch from A to B. Now we have a circuit that has only a resistor and an inductor in it with no battery remaining. And of course, what you might expect, just as in the case of a discharging capacitor, we should see an exponential decay in the current in the circuit, and that's exactly what we're going to see. We can show it by writing Kirchhoff's loop rule for the resistor and the inductor, separate variables, and I solve for the current as a function of time, and of course you can see that the current is decaying in the circuit, just as the charge decays in a decaying RC circuit. Not surprising, again. So this is 2 ways of looking at it. One, a charging case where I put the battery in the circuit, and the second part we have a discharging case, or the equivalent, where we only have the resistor and the inductor in the circuit. Let's do an example. In this case, let's do it for the earlier case where the battery was in the circuit. Let's talk about a circuit where the current is building up. Suppose I have an RL circuit with a battery 12 volts, I've got a resistor of 8 ohms, and an inductor of 20 millihenries. Okay? And let's find the current let's find the current at 5 milliseconds. So let's find the current. Okay? First thing we're going to do, let's calculate the inductive time constant. Tau sub L is L over R. I put that together, and I'm going to find that that's going to be 2.5 milliseconds. Now I can find the current as a function of time. That's going to be E over R times 1 minus e to the minus t, which is going to be 5 milliseconds over 2.5 milliseconds, t over tau. And I put my numbers in, and lo and behold, I calculate a current of 1.3 amps at 5 milliseconds. So that's a very simple example of that. We can also do the following. There's a sort of an interesting wrinkle to this. We could say, at what time will the voltage in the circuit be equal to or I should say the voltage across the inductor be equal to the voltage across the resistor? Now, this is what you might equate to a half-life. In fact, we know that the time for a half-life is just equal to 0.693, which is log of 2, times the inductive time constant. So I can write that as 0.693 times my inductive time constant, 2.5 times 10 to the minus 3 seconds, and that's going to be 1.73 milliseconds. So that's the time at which the voltage across the resistor and the voltage across the inductor are going to be the same. Let's see if that's true. Suppose I write it out. 12 times e to the minus 1.73 divided by 2.5, is that right? Sure enough, 6 volts. So the voltage across the inductor and across the resistor are going to be the same. Very nice. I'm going to switch gears a little bit, because this is sort of while it's an applied example using inductors, this has more far-reaching consequences than you might think. And we'll see a lot of this as we go deeper into the course. Let's talk about the energy in an inductor or in an RL circuit. Let me give you a little hint. We did the same sort of exercise with capacitors before, and what we found was that the energy, potential energy, electrostatic potential energy, was stored in the electric field of the capacitor for an RC circuit. With an RL circuit, then you might say, well, I'll bet you the energy is stored in the magnetic field of the inductor, and you're going to be 100% right. So let's look at that. Now, in an RL circuit, to be precise, we do have some dissipation of energy through the resistor, of course. But we also have what energy is not dissipated in the resistor we fully expect is going to be stored as potential energy in the magnetic field of the inductor. How do we show this? Let's do the following. Let's write our Kirchhoff equation. But let's talk about the rate at which energy is expended. Let's make this a power equation. We can do that by multiplying by I, each term by I. Notice, this is the power. This is essentially V equals IR, the power that's generated by the battery. This is the energy that's dissipated per time through the resistor. And of course, this is what we would expect to be the energy that's stored in the inductor. It's basically a conservation of energy term. Let's look at the inductor term more carefully. I'm going to write that energy that's stored as du sub B, in other words, potential energy due to the magnetic field, or stored in the magnetic field of the inductor. I'm going to write that as Li/dIdt. And this is the rate at which energy is provided to the magnetic field of the inductor. I'm going to integrate both sides, and notice what happens. I'm going to get that my energy is going to be equal to 1/2 Li squared. This is the energy stored in the magnetic field of the conductor. You might remember this is very similar to what we found with RC circuits and capacitors, 1/2 CV squared. Very, very similar expression. What I'd like to do is take this a step further because it makes the problem even more interesting. Let's find the energy density, the energy per unit volume, stored in a solenoid. So remember, energy density, that's little u sub B, is equal to the energy divided by the volume, or the area times the length. So let's do this for a solenoid. I know that the inductance for a solenoid is mu naught times little n squared, the number of turns per length, times A times L. The magnetic field for the solenoid is mu naught times little n times I. So the energy stored in the magnetic field of the solenoid would be 1/2 Li squared. And put all that together, I'm going to get that it's 1/2 mu naught n squared A times L. Now A times L, of course, is a volume. And so what we have then, I can also, yes, let me not forget, my current I can write as the magnetic field divided by mu naught times little n, write that squared, I want to leave that out. Notice what I have, my mu naughts go away, one of my n's goes away, and I get the following. I have that this is b squared over 2 mu naught times essentially a volume, a length times an area. That tells me that my energy density is going to be equal to, that's energy per volume, 1/2 b squared over mu naught. So this is the energy that's stored, the energy density of the magnetic field in the solenoid. By the way, this is not just applicable to solenoids, this is true in general. And so again, we have an equation that's very, very similar to what happens with energy stored in an electric field. The energy density for electric fields is 1/2 epsilon naught E squared. Energy density for magnetic field, 1/2 B squared over mu naught. So you can see the similarity in those two expressions. We have said all along that by the end of the course, we're going to unify electricity and magnetism, and you're seeing kind of how we may be approaching that. We're not there yet, but we will get there. And as I say, in the case, we did it for capacitors, but we said in general for electric fields, that's an energy density. In general, this is true for magnetic fields. It doesn't have to be a solenoid, but that's a very nice example to show it. One last topic I'd like to do in inductance is something called mutual inductance. So suppose I have two circuits. Suppose I have two circuits that have a current going through them. What can happen is the current in one circuit, of course, will produce a magnetic field that affects the other circuit and the current in the other circuit. We call this effect mutual inductance. And it's represented in this way. I can write this effect of, let's say this is coil 1 and coil 2. The mutual inductance of the effect of coil 1 on coil 2 can be written as number of turns in coil 2 times the magnetic flux caused by coil 1 on coil 2 divided by the current in coil 1. So this represents a magnetic flux caused by a current in coil 1, which has N1 turns, passing through coil 2, which has N2 turns. If the current varies in time, the EMF induced by coil 1 and coil 2 is just going to be, I'll write that as E2 minus N1 D, I'm sorry, minus N2 is going through coil 2, dP12 dt, which I can write as minus N2 d dt of M12 I1 over N2. And of course that looks like minus M12 di dt. No surprise, we can switch the situation and look at the effect on coil 1 from coil 2, and you're going to get the same exact answer. Well, essentially the same exact answer. It would be minus M21 di2, this was di1, dt. That being the case, because the effect is exactly the same, M1 is equal, M12 equals M21, it's just equal to M. And we can very simply say that if I want to look at the EMF induced in coil 2, I can write that as minus M di1 dt, and similarly, the EMF induced in coil 1 would be minus M di2 dt. Very simple arrangement. And so we call this mutual inductance. That is, I have two coils where I have currents going through them.